Lagrange multipliers. Find the minimum distance from the orange to the point of the straight line x plus y is equal 1. So what you want is have a straight line here, okay? This is a straight line, and go there, go there. Okay, this is x, this is y. This is a point P over here, x and y. This is orange, point 0, 0. So the distance will be x squared plus y squared. You see, this is x and this is y. So this distance over here, this distance here is square. You see the OP, this is equal OP square. See, the distance square is x squared plus y squared. Okay. Now, there is a constraint. X plus y is 1. So this is the constraint. Because it is imposed that the point must lie on this straight line. So this straight line x plus y is equal 1. So here is a point, this point here is a point 1, 0, and this one is a point 0, 1. So 0 plus 1 is 1, 1 plus 0 is 1. So this is a straight line, x plus y is equal 1. So what Lagrange multiplies says that here you have d squared plus this Lagrange multiplier times x plus y. This is equal to x squared plus y squared plus lambda x plus y is equal, let's call f x, y, and lambda. See? Now, let's minimize or maximize this function over here. So, partial of f to respect to x is equal, this is 2x plus lambda. You see? Now, partial of f respect to y is equal to y plus lambda. You see? The partial derivative with respect to y is 2y. Lambda y, the partial derivative will be lambda, so this has to be equal 0, 0, and finally, partial f with respect to lambda is equal, now, this is be x plus y, so this will be equal 0. Now, let's do as follows. From here, lambda is equal minus 2x, and here lambda is equal minus 2y. So x is equal minus lambda over 2. This is y is equal minus lambda over 2. So let's plug this x and y. So x plus y is equal 1. Then x is minus lambda over 2 minus lambda over 2 is equal 1. So this implies that lambda is equal minus 1. You see? Because minus 1 is 1/2 plus 1/2 is equal 1. So if its lambda is equal minus 1, you see x will be minus 1, so this implies that x will be half and y will be half. So for this value, the distance, you see this or the square distance, okay, you could find, okay, the minimum distance could be d or d square, it's the same, you see. Now, so d square will be, now let's substitute x and y over here, 1/2 square plus 1/2 square. So this is 1/4 plus 1/4, so this will be 1/2, because this 1 divided by 4 plus 1 divided by 4 is 2 divided by 4 is 1/2. So d is equal is square root of 1/2, so square root of 2 divided by 2. So this is d. You see, you can see clearly here, see, that this is a straight line, this is 1, you see, this is 1/2, so this is x, this is 1/2 here, and here is 1/2, see? So this distance over here is the minimum distance, is this square by this square. So d is equal to square root of 1/2 square plus 1/2 square. See, this will be square root of 2. See, now this is d. So that's the minimum distance. We will use Lagrange multiplier in the next step. One is interested in finding the minimum or maximum value of the shear stress tau s. Now, you see, the shear stress tau s, we see here case A and case B. In the case A, we work with x1, x2, and x3. And case B is x1 asterisk, x2 asterisk, x3 asterisk. So here we are working in the principal directions. Okay? This is eigenvector, and eigenvector. So because we are working the stress tensor, I guarantee that these eigenvectors, they are orthogonal, and we can make the eigenvector unit vector, unit eigenvector. So these are principal directions, see here. And here's x1, x2, and x3. Now, case A and case B. I will start with the case A. You see that this expression for tau s, the square, has a lot of terms here. Much more terms than in case B, as it will be shown. Now, you see, the stress vector, first of all, sigma n, you see, is the projection of the stress. This is the stress vector. It's the projected stress vector lying in the normal to the plane. You see, there's a normal to the plane, a normal to the plane. And this is sigma n. And this is tau s. You can see clearly here that, you see, this square, this magnitude square plus this magnitude square is equal to this magnitude square here. So to get the magnitude of this dt, you just t dot t. T dot t is the magnitude of this length squared. Now sigma n is the projection, so t dot n is sigma n. So sigma n squared plus tau s squared is equal to t dot t. Obviously, tau s squared will be this length, okay, minus sigma n squared. Let's forget for a while this here. Now, we can see also here that t and n, they are the same. So they do not depend on the coordinate system. You see, t, the stress vector, and the normal, okay, to the plane, they don't depend on the coordinate system. If it's principal direction, or it is x1, x2, x3, or any other coordinate system, t and n, you see, they are the same. Now, the components are different, okay? The component of n on this system is completely different of the component of the same n on this system over here, on the same t, okay? So t dot n, sigma n, I can obtain sigma n using this system here or this system over here, exactly like we did in the last lecture. Last lecture, we calculate sigma n using these two different coordinate systems. We got the same result. It's a minus 29 over 2, I think. Now, go there and see it. Now, you see, I'll show you to get tau s squared using A, the section A, you'll be quite, not confused, but it's quite long because they have a lot of terms. So, how do I get the stress vector? Okay, this is N1, N2, N3. This is the stress tensor, sigma ij over here. You see? Now just multiply. You see, first row, first column. This will be T1. First row, second column will be T2. This first row, third column will be T3. So put Ti over here. So there's a sum. Okay? For I is equal 1, you put 1 here, 1 here, and 1 here. For I is equal 2, 2 here, 2 and 2, because I is a free index. But this is a sum. You see, 1, 1, 2, 2, and 3, 3. So it's Nj sigma Ji. You see, any J sigma Ji represent any of these three components of the stress tensor T. Sigma n is T dot n. You see, T dot T is Nj sigma Ji. You see, there's a scalar. You see, there's a scalar, so this is Ni. You see how many terms do I have here? I just sum J for 1, 1, 2, 2, 3, 3, and I 1, 1, 2, 2, 3, 3. So this it has a lot of terms. So tau s squared is Ti is T dot T minus sigma n squared. Now there is a constraint. A constraint, what means? Any 1 squared plus any 2 squared plus any 3 squared is equal 1. So, like we did in the example about Lagrange multiplier, just previously in this lecture, I'll do the same. So, lambda is a Lagrange multiplier. So, lambda is Lagrange multiplier. That's right here, multiplier. See? Now, I can now minimize tau s squared. I will not do it because I will express the same tau s squared, which does not depend on the system. That's why I put this picture here in the middle. You see? This belongs to A, the section A and the section B, the same. You see? T, tau s, sigma n, and T and n, they do not depend on the system. So I will find another simpler way to express tau s squared, the same tau s squared, using the principal direction. Okay, I'll not minimize this. Okay, using obviously the same constraint. Okay. Case B, this case here, let's use the system, the coordinate system, as the principal direction. So the eigenvector, unit eigenvector. Now T1, T2, T3. Now I'll put the asterisk here. See. Because the components of this system are completely different from the components of this, but the vector is the same. You see, the vector is the same. Case A and case B. Now, and also the components, you see, are different. Now, here is the stress tensor in this direction over here. So in this direction, the shear stress, okay, in the 1, 2, and 3 direction, they are 0. So now we can multiply here. This will be like this. You see, the simple is the expression for T1, T2, and 3 is much more simpler. Now sigma n is t dot n. You see, I don't put asterisk here, neither here, because they are not, they don't depend on the coordinate system, but the coordinate, yes. You see this here, see, now, you see, the components are different. Now here I have this, you see, the magnitude of t is ti, now using the new component with respect to the principal directions. So this will be like this, and this will be like this, you see. Now sigma n square is this here, is square. I can substitute t1 here, you see. Look, I can substitute t1 asterisk right over here, so this will be equal to, let's write right here, you see, t1 is sigma 1 n1, so this will be t1 n1 asterisk square plus, let's write here, t2, I'm sorry, this not t1, this sigma 1. You see, because t1 is sigma 1 nu1, so sigma 1 nu1, sigma 1 nu1 square plus sigma 2 nu2 square plus sigma 3 nu3 square. So this is sigma n expressed in this principal direction, in this coordinate system. So this expression here, you see, it will be simpler, much simpler than if we work with this system over here. And tau s is the same, you see. Now the unknown here is this vector n, you see, this unknown here, you see. I want to know, you see, which plane, okay, exists such that tau s square is minimal, you see. So you see clearly when you change the plane, you change n, so that's n is unknown. If you change n, you change the projection, you change t also, you see. T, I'm sorry, if you change the plane, t is the same, n is the same. But if you change the plane, n will be different and t will be different. For a fixed plane, you see, tau s and sigma n are the same. But here I'm not interested in the fixed plane because n is unknown. So there is a plane such that n and t make the tau s as a minimum value. So let's find out which n exists such that tau s will be a minimum. Okay, let's go back to work. Now, partial derivative tau s square respect to nu1 is equal. So this will be 2. This will be nu1, here will be nu1 square, sigma 1 square. So this will be 2 nu1 sigma 1 square. You see, because sigma 1 square is constant. This is 0. And here will be, let's call this here as e, okay? This will be minus 2e. Now, the derivative inside here will be respect to nu1. And this will be 2 nu1 sigma 1. Sigma 1 is constant. This is 0, so this is enough. Now here is lambda nu1 is squared, so this will be plus 2 lambda nu1. So the partial derivative of this function will be 0. Now the partial derivative with respect to n2 will be analogous to that. So this will be 2 nu2 sigma 2 square minus 2e 2 nu2 sigma 2 plus 2 lambda nu2 is equal 0. See? Now, this is equal 0, so let's divide by 2n1. You see, 2n1, 2 here, n1 here, and this is 2n1. And here 2n2, you see, 2n2 and 2n2. So we have this system here, sigma 1 is square minus, you see this is 2 over here, 2e sigma 1 plus lambda is equal 0. Here sigma 2 is square minus 2e sigma 2 plus lambda is equal 0. Exactly like we did previously in this lecture, let's get lambda here and substitute there. So this is lambda is equal minus sigma 2 square plus 2e sigma 2. See? Sigma 2 square, that's sigma 2. Let's increase here. Let's substitute on the first relation. So sigma 1 square minus 2e sigma 1 plus lambda. This will be minus sigma 2 square plus 2e sigma 2. This will be 0. So this is sigma 1. No, here I can write like this. This is sigma 1 is square minus sigma 2 squared. This here. Now this I will put plus 2e. Now I put sigma 1 minus sigma 2. Let's put here. So let's put minus here. Then I put sigma 1 minus sigma 2. You see, I combine this term with this term. So this will be 0. So this is sigma 1 plus sigma 2 that multiplies sigma 1 minus sigma 2. So if I simplify this with this, I'll get here sigma 1 plus sigma 2. You see? Now, I can write that 2e is equal sigma 1 plus sigma 2. Now let's substitute e over here, and knowing that n2 is equal n1 square 1 minus n1 square. See? Now let's develop here. Substituting now, this sigma 1 plus sigma 2 is equal, or minus 2e is equal 0. So sigma 1 plus sigma 2 minus 2e. You see? Now here I already substitute n2 by 1 minus n1 squared is equal 0. So it's very simple manipulation. Okay, you can manipulate this very easy. So this is minus sigma 1 n1 squared minus 2 sigma 2 minus 2 is this. Let's multiply sigma. This is sigma 1 minus sigma 1 squared. So this is minus over here. So this will be minus 2 sigma 2 over here. You see? Plus, you see, plus 2 n1 squared sigma 2. Now sigma 1 minus sigma 2. See, sigma 2 minus 2 sigma 2 is minus sigma 2. So minus 2. Now I put sigma 1 minus sigma 2 here, just a factor. This n1 squared is equal 0. So since sigma 1 is different from sigma 2, I can simplify. So 1 minus 2 n1 squared is equal 0. So n1 squared is 1/2. n2 squared is also 1/2. Why? Because n1 plus n2 is equal 1. So n1 is plus or minus square root of 2 divided by 2. Likewise, n2 is equal plus or minus square root of 2 divided by 2. Now, if I substitute here, I will get the minimum or maximum stress. The minimum stress is for n1 is equal, n2 is equal 0. So let's substitute to get the maximum tau s squared. You see n1 and n2, the unknowns. Now are calculated. So let's get tau s squared. Substitute any1 is equal any1 square inside the function, then you get a very simple relation, you see? Now you can see here that tau s maximum is plus or minus sigma 1 minus sigma 2 divided by 2. It's very simple, okay, manipulation here.